Okay, welcome everyone again to this retronet call on PCM30 trunk technology and channel-associated signaling. I didn't put my usual disclaimer slide in the beginning, or the slide that I often have in my presentations, but let me do it verbally. So I'm not an expert in this topic. I've never worked with this type of equipment back in the day. With various other equipment, but not with this kind of transmission equipment. So for sure, there are people who have more operational or practical knowledge about it. All this has been done mostly as theoretical research based on documentation and general knowledge about TDM technology. So if anything stands to be corrected, I'm very happy to receive your comments or corrections to that. So I have this one slide where we are coming from, and that's sort of from the Osmocom community, where sort of also this retro networking group has spun off. In this context, we basically know E1 as a carrier for ISDN primary rate services, or for frame relay, for example, or various different cellular-specific interfaces like the ABIS interface or the GB interface, which are all carried traditionally over E1 circuits. Or even circuit switched SS7. What all of those, well, excluding frame relay, which is sort of an outlier, but in general they have in common is that we have the not the channel associated signaling, but the central channel signaling. So we have a dedicated time slot with a signaling protocol with messages on it and so on that handles the signaling of the related calls or related protocols on it. Whereas today we will talk about the predecessor technology using channel-associated signaling and a PCM30 technology. So if we look at classic PSTN networks, public switch telephony networks, then we have a couple of major components. Of course, there are more, but we have, well, the telephone switch or exchange or central office, depending on the region of language you are coming from, which has the purpose of, well, as the name says, switching calls based on numbers you dial or signal to the switch. And then you as the subscriber at home, you have something called the local loop, which is the line that connects the switch with you as the subscriber, the last mile also sometimes how it's referred to. And then, of course, there's not just one switch, but there's multiple switches and different types of switches, and they're interconnected with trunks that are connections between switches, so not between a subscriber and a switch, but between trunks. And of course, well, traditionally, those were also just copper pair wires, but let me say 3-wire, 4-wire interfaces, also 2-wire interfaces. But if you use those same wires that you use for the local loop, then we have, of course, transmission problems with attenuation and noise in the line, and you need to do amplification, and then you also amplify the noise, and the quality gets worse, and you have crosstalk between different lines, and so on and so on. So over time, well, transmission technology was introduced for those trunks, and transmission technology before TDM and PCM systems came out, basically the two general mechanisms used is on the one hand a baseband transmission, or in German NF or Niederfrequenz systems, which is the simplest form of transmission. It's just the analog signal. They come in different flavors. It could be DC coupled, it could be AC coupled. You could have amplification if the distance is longer, and yeah, you have, of course, signal quality issues with the longer the lines get. Another system that was used for a very long time is the so-called carrier frequency transmission, or Trägerfrequenzsystem, or TF in German, which is what Gutzkopf has briefly shown, the one cabinet in his location in the background. And in this case, you're modulating analog voice signal to a carrier, just like you would do in radio transmission, modulating a radio signal over a carrier. And you put many different carriers on different frequencies. And overall, you can carry lots of phone calls over a single pair of coaxial wires or microwave links or similar things. But it's all done completely in the analog domain. I'm not an expert on this, but I think there were like TF systems with 2,700 calls or something like that. As Michaela points out, it's called frequency division multiplexing FDM in American telecom culture. And Christoph says, okay, up to 14,400 carrier frequencies. Yeah. So this was all done using discrete modulators, demodulators. So you have really large cabinets with lots of components that do all this modulation and demodulation for all of those different carriers. And yeah, it has, well, this is a German slide, a diagram taken from a book that compares these different mechanisms. So the assumption is on the left-hand side, you have some kind of analog switch. And on the right-hand side, you have another analog switch. And you can either have the galvanic coupled baseband signal in the first case, or you have the AC coupled two-wire transmission in baseband here in the second line. And the third one is the carrier frequency or FDM system. And then at the bottom, we have the PCM system, the pulse code modulation, with the signal translator, the Kennzeichenumsetzer, which we will talk about later on as well. So, and all of these can be used interchangeable. The general problem these systems solved is always the same. You have multiple telephone switches, and they need to be interconnected somehow in order to make calls between those switches. The history, as far as I could research it on PCM and PCM30 technology, actually it goes back to 1926, where a Paul M. Rainey of Western Electric patented a facsimile system using 5-bit PCM. It was well, a facsimile system, so not for voice, so slightly different, but it's the first PCM reference that I could find. And then we have various different other people involved. Alec Reeves developed pulse code modulation for voice telephony. There's a couple of patents in 1938, 1943. In 1946, there's a patent communication system employing pulse code modulation from Bernard M. Oliver and Claude Shannon, famously. And yeah, like in this time from the 20s to the 40s, probably also in the 50s, the big problem was how to implement those technologies. Of course, there were no semiconductors yet, and no integrated circuits, of course. And even the problem of doing analog digital or digital analog conversion was a big challenge, and they developed special cathode ray tubes for these kind of topics. You can find some interesting old papers if you want to research more on that. I just have looked at it very briefly. The PCM systems like we know it today started to come out in the 1960s. I'm talking about commercial applications here. I'm not sure what the military had at some point earlier maybe, but so the T1 carrier system with 24 channels developed by the Bell Labs in the US is the system that's deployed in US, Canada, and Japan. 5 years later, Fujitsu domestically in Japan delivers the first PCM24 digital transmission equipment to NTT, the Japanese telecom company. And in Germany, we had the first trials in 1967. With different vendors, PCM30 equipment. 1968 is allegedly when the E1 32-channel system was specified at CCITT, which is was deployed basically in the rest of the world, except the US, Canada, and Japan, where T1 is used. And actually that's a typo. 1969 is supposed that, not 96. So in 1969, there were already 21,000 PCM transmission systems deployed in the US. I didn't really quickly find statistics for other countries, but it's massive growth if you think like it was developed in 1961 and in 69, 8 years later, you have already 20,000 such transmission systems deployed. So operationally, well, let's skip that. So what back in the day in 1970, so briefly after the introduction or the tests in Germany, I found a reference that says, based on the cost of the equipment, it was economic to do it from distances larger than 10 kilometers. So if you were below 10 kilometers, some of the analog systems made more sense, but if you went above 10 kilometers in 1970, then it was economically better, so cheaper to do PCM30 at that point. Of course, that with further integration and improvement of electronics, that has likely changed significantly in later years. So what kind of vendors did we have in Germany? These 4 vendors were suppliers to Deutsche Telekom, supplying PCM30 equipment. At least those are the 4 that are always mentioned in the documents I have from Deutsche Bundespost. There might have been others, but at least those are documented suppliers. And if we look at a slightly more verbose block diagram, in this block diagram, we see sort of, well, on the left-hand side, it's not really drawn, and on the right-hand side, outside of the picture, are the 2 switches, and then this is the PCM30 equipment. So we have the KZU, the Kennzeichenumsetzer, which is converting the signaling, with the MUX, the multiplexer, and the LE, which is the line transmission equipment. And then in the path between the 2 switches, we might have these regenerators, basically decoding the signal digitally and reclocking and retransmitting it, the bits, to get over higher distances. Those regenerators you needed depending on the type of line you had and depending on transmission medium, but the references I found in the early days, in late 60s, early 70s, they said, well, in the worst case, they needed regenerators every 2 kilometers, and for better lines, it was basically at larger distances, assuming 2-wire copper transmissions here. Yeah, so I think let's maybe quickly look at the case, the interfaces. So on the interface number 1 is the analog interface to the telephone switch. Interface number 2 is still an analog interface into the multiplexer. The multiplexer then is it's multiplexing, and on item number 4 we have the 2 megabit interface. I guess this interface 4, and we will get back to that, is sort of what we could interface with a modern E1 interface. And then we have the line transmission equipment, which builds the interface that actually goes over the copper wires here. So yeah, this is just another diagram to show at the regenerators. So we have basically the end unit on the left and on the right hand side, and in the transmission line, depending on the distance, we have these regenerators. And again, if it's not clear, I guess to most people it will be clear, but the advantage of having, let's say, analog transmission and analog amplifiers is, of course, that the digital regenerator can do lossless regeneration. So you can have as many as you want, and the signal will not deteriorate, as unlike analog transmission with analog amplifiers, where every time you amplify, you get new distortion, and you amplify noise that was present on the input and amplify that to the output, and so on. So yeah, let's look at the time slots. I suppose everybody knows that the E1 interface has 32 time slots and so on. And this is, if you've ever worked with ISDN primary rate or something, that's not new. Like we know it from E1 ISDN primary rate circuits, time slot 0 is for framing, multi-frame alignment, CIC4 and alarms. I think in the documents I found about the use in Germany by Deutsche Bundespost, CIC4 was always used in the equipment. I don't think it's even possible to switch off. And then we have 30 time slots, which is 1 to 15 and 17 to 31. Again, like an ISDN primary rate, are used for the analog voice telephony. At that point, it was literally analog voice telephony, or maybe analog fax at some point, and analog modems, but basically telephony. And the signal on those time slots is exactly the same as, again, we know from ISDN. So with the usual 64 kilobit slots with 8 kilosamples at 8 bit. With A-law on this side of the planet. And again, and I always say it's like ISDN. Of course, technologically, this all predates ISDN. So ISDN was basically recycling all that PCM30 technology that was already used in the transmission equipment between switches, and it started to use it in the subscriber line, at least for the larger subscribers, the primary subscribers. So technologically, it's the other way around. It's just that since we youngsters are coming from a day where all we know is ISDN, basically, and now we look back in history, and then I'm saying, well, it's the same like ISDN. And on Timeslot 16, we have this channel-associated signaling, which is not like ISDN or SS7, where we actually have a layer 2 and layer 3 protocol stack and messages being exchanged, like a modern packet-switched data network. But instead, it's a continuous stream of 4-bit signaling words for each of the 30 voice time slots. And this is structured like seen in this diagram. So on the top, we see the E1 frame, which has 31 time slots, and time slot 16 is the signaling slot. And if we concatenate 16 of those signaling slots, we get the multiframe that's used in the PCM30 system. And in there, time slot 0 has this frame alignment signal and a service word where you can signal alarms, pretty much like the time slot 0 at the higher level. And then you have 15 remaining bytes. Each of those is split into 2 nibbles, and each of those nibbles has a 4-bit signaling word for each of the 30 time slots that you have. And if you do the math, this means you get a 500 hertz rate of those signaling bits. So 500 times per second, you have ABCD bits, meaning every 2 milliseconds, an ABCD change could happen. And those bits really, they're not used for any kind of complex protocol or something. It's really just indicating a state at the analog line equipment, or a request of what kind of state is to be applied to the line. And that's it. And it basically becomes effective immediately at the other end when you set those bits respectively. So, and now what do we put in those bits? And that's then what the signal converter or Kennzeichenumsetzer in German does. So we have analog line conditions, well, the simplest one, on hook, off hook, but then we have pulse generation, pulse detection, and flash, and all kinds of things. And those conditions depend, of course, a bit on the type of analog interface that you have. Some conditions may not exist in all of those, and some are specific, and so on. And then you have to differentiate between sending and receiving lines in there. The Kennzeichenumsetzer is converting those signals to those signal words. The 500 hertz rate I already stated. And when there's different signal coding that now defines what those bits mean, that's a German diagram from a book that doesn't actually say for which analog interface it describes this, which I find quite funny. This one is taken from a Siemens booklet that documents the R2D signaling system, which I believe was used in east of Germany after German reunification, at least, maybe in other cases. And it defines here the ABCD bits for the respective condition operating condition. So that sort of depends on the specific analog interface and the standard that it applies to, but all of the previous bits up to here basically are all universal for all of these PCM30 equipment types. I think there are some differences in how those A and N bits are used between the equipment called PCM30/32, which is the earliest equipment used by Deutsche Bundespost in Germany, and later equipment which was just called PCM30 without the /32. There were some minor differences here, but it's like, And also in general, irrespective of the vendor, all the interfaces, the electrical interfaces and the signaling was standardized, so you could I'm not sure whether this was done operationally, but at least according to the specs and the standards, all should be interchangeable and interoperable between different vendors that were used. So yeah, that's a picture from Fernmeldemuseum Dresden of the PCM30 equipment by Siemens. It was always done in these high racks. That's typical for German telecom installations. So 2.30 meters high, and in this case very narrow, only 22 centimeters. And yeah, here you can see the individual modules for each of the time slots in one such unit, and so on. And this likewise, we have a picture of the corresponding Philips equipment, which all looks very similar. In the end, you always have your modules for the individual analog lines that plug into some kind of rack. Yeah. That's it in terms of the introduction. And now, what kind of use cases did we see? What did people want to do? So on the one hand side, there's the request to carry PCM30 over TDM over IP with ICE1 USB, for example. So you would have PCM equipment on both sides, and rather than having a copper line or whatever other line directly connecting those two devices, you go into an ICE1 USB and use the TDM over IP protocol to the other side. I don't really see any reason why that shouldn't work.
It's not, I'm sorry, I tried it out.
Yeah, but based on everything that's visible from the documentation, there is no reason why it shouldn't work.
Yeah, we can discuss.
Sorry?
We can discuss later.
Yeah.
It's a subtlety.
Yeah, but basically, I mean, there were questions about alignment and so on. They all don't matter in this context, I think, as we just, well, anyway.
It's an alignment issue.
So
the multiframe need to be aligned with the inner signaling frame, but yeah, that's very technical.
Yeah, the other side is sort of for the other use case, and that's one that I'm more interested in personally, and some other people as well, is to sort of use only one PCM30 termination equipment and then have a computer at the other end. So basically use this as a way to interface analog switches with a digital switch, digital soft switch. And in this case, basically we only have one ICE1 USB or DAHDI card or whatever, and the PCM30 equipment at the other end. So the soft switch needs to interpret and generate those TS16 signals. That's basically all there is. Now the question is how to do it in the detail. Devil is always in the details. So theoretically, the E1 multiframe alignment needs to know the TS16 alignment, or basically it's needed, but the ICE1 USB doesn't preserve that alignment. But practically, as has been discovered recently, the Timeslot 16 contains the pattern itself. The signaling frame starts with 4 0 bits, and then this 1 A and 1 bit pattern where A and N are alert related bits. And then all other frames in ABCD bits should not use 0 0 0. That's even in G7. I think I didn't include that screenshot, but ITUT G704 states that an all 0 bit pattern should not be used for the ABCD bits. It doesn't say it must not, but it should not. And at least in those tables that we've seen, we have concluded that it's not the case. So basically, one can just look at TS16 and look for that repeating sequence of 4 0 bits in the upper nibble every 16 slots, and use that to achieve alignment to this signaling frame, these 4 bits here. And once we are aligned, then we can know which bits correspond to which voice channel and associate that. So that should be trivial.
But that's actually the problem, because the other side is the PCM30 equipment. And the PCM30 equipment does not look at that 00 bit pattern, but it just looks at the multiframe number. And when you're sending that pattern, you don't know how you end up being aligned in the multiframe.
Okay, yeah, we can talk about that. So assuming or ignoring even the ICE1 USB specifically, looking in general how to interface then with soft switch software. I looked a bit into DAHDI, and at least what I saw in stock DAHDI was not very convincing. So the way how I could find it, and again, if somebody knows something else or knows more about this, I'm very happy to hear about it. But in general, of course, DAHDI supports channel-associated signaling. Anyone who's ever done a system.conf for DAHDI knows you can set CCS or CAS on an E1 or T1 trunk. And the way how, when looking at the driver, this seems to be implemented that the framer chip or controller, E1 controller in the hardware of the TDM cards that Digium produced supports this directly. So when you set those bits on a channel in DAHDI, then it basically ends up in a write, a register write or something on the framer. And in the receive direction, whenever the ABDCD bits of a given channel change, then there is an event that is signaled on the DAHDI channel. The problem is, well, the nice part is that it implements this demultiplexing. So you do not open that DS16 and do the demultiplexing yourself, but rather it's inside the driver. And let's say you open the DAHDI channel for Timeslot 5. Then in that Timeslot 5 device, they have a mechanism. I think they return a negative result code when reading from the device or something, and then this the application should know that in this case it should call a specific I/O control to fetch an event, and that event then will say bits changed, and basically tell the user space program, the soft switch in this case, that these ABCD bits have changed. The problem, of course, here is that you cannot, like from the DAHDI or from the driver side, you cannot really know how often or how reliably, time-wise, the soft switch will pull those bits, will sort of realize that it needs to detect this event and retrieve the event using the I/O control and then know it. And for something that is rather asynchronous and slow, like an on-hook, off-hook, or whatever event, that I think is fine. And for DTMF dialing, then in-band, like it's used a lot in American, North American sphere, or was used, that's fine. But I'm a bit doubtful if this mechanism would be good enough for reliably generating or counting dialing pulses.
There is a part in the general DAHDI that does the counting and generating pulses.
For the digital trunk cards, or just for the analog ones?
It never leaves the kernel space. It looks into these bits that come from the driver of the TDM card, and then already does the counting and generating pulses in a general manner on the ABCD bits. I don't remember how it's signaled then also with an IOCTL or something, but the counting and the time-sensitive thing can be done in the kernel. I also think there is a pound if def around, but it's implemented.
Yeah, I saw a lot of this in the branch from the Connections Museum. So they do a lot of, I saw basically this patch doing it, but I didn't really see that in the original normal upstream DAHDI, but it could very well.
I tried it out with upstream standard DAHDI, over a T1 where the bits get transmitted a little bit differently, and I could regular dial pulsing worked.
Okay, good. Yeah, then there's a code path that I didn't see in my analysis, and that's good, because I was about to say, well, this is how it needs to be done. You want the timing critical parts inside the kernel, and then get the resulting digits out to user space. And having all this demultiplexing and multiplexing inside DAHDI makes a lot of sense inside the kernel. So you have it somehow associated to each and every of your 30 B channels in ISDN speak. So that makes a lot of sense to me. So I think for this use case, one of the first steps then would be to make sure that this can also be supported with IS1 USB, and compare that the behavior is identical to that of a Digium card. Because so far the DAHDI driver for IS1 USB has only been tested with basically SS7 and ISDN and frame relay, but never with so always with CCS and never with CAS. So I'm quite sure it doesn't support this in the kernel driver, and that needs to be added for that use case. Okay, yeah. So two book references for German books that go into detail on this. The first one is this 1,300-page monument about all the different PCM technology from the different vendors used in the German telecom. So that is highly recommended. And a slightly older and lower page count one in the second slide. Yeah, that's it for what I wanted to present, and we can go into discussion. Maybe before we go into the alignment issues with IS1 USB, does anyone have other questions or comments on the topic so far? Thanks to MFM has mentioned that there's a YouTube video by Sarah Autumn who did the Connections Museum DAHDI modifications. That's appreciated. Thanks. I didn't know about the presentation. I knew that she did it, and I saw the code, but I didn't know there was a video presentation about it. I'll certainly have a look at that. Thanks for sharing. Okay, yeah, then we can go into the alignment discussion. We're still on the record. If that's okay with everyone, we can keep it that way, I think. But if somebody would rather have their comments or discussion off the record, then I'm also happy to switch it off. So just let me know. Okay, no comment. So no complaint so far. No protest against keeping it on the record. Okay, TNT is also here. That's great. Typing something. Do we have an official spec? Well, actually, let me quickly. I think G704 is actually sufficient. There is this one note here. That's basically, so this is table 14 that says, well, this is how the channel associated signaling works on Timeslot 16. And we see that there's Timeslot 16 starts with 4 bits, and it says somewhere, it is recommended that the combination of 0 bits A, B, C, and D should not be used for signaling purposes for channels 1 to 15. Well, 1 to 15 at least, not for 16 and higher, but based on this, we can recover in the receive direction. We can actually recover the alignment by solely looking at Timeslot 16 without looking at the Timeslot 0 multiframe alignment. But as Christoph pointed out, the transmit direction then, of course, is a problem. If the receiving
table in G04 gives it that it needs to be connected, there is an indication that says Timeslot 16 in frame 0 and so on.
Yes, it is. It is specified. I agree. It is specified that it's in Timeslot 0, but then it's a bit strange that there's another alignment pattern, but then it's supposed to be aligned anyway. So why have another alignment pattern? But okay.
I agree, and I went through the whole same thing. I was like, yeah, well, what do I do? I can't do it with ICE1 USB. Then, I discovered the zeros, and then found out when I tried it that, actually the other side doesn't like to be misaligned with the multiframe. And even if it weren't specified, that's how Digium implements it in their hardware. And I'm pretty sure that the PCM30 that I've seen at No One's Place implements it this way. So we can't get around in connecting the two things somehow.
Yeah.
But I also tried to read a little bit the firmware of the ICE1 USB. I had the impression that the multiframe number was already known internally.
Yeah. So the hardware of the firmware absolutely knows what multiframe is being transmitted, simply because the actual hardware that's implemented in the FPGA takes entire multiframe as a block. So you don't submit frame by frame, you submit an entire multiframe. So the firmware absolutely knows the alignment. And for the receive part, it's actually already in the header that is sent from the ICE1 USB to the host. It's already included. For the transmit direction, it's just currently ignored. I mean, at the moment, you know that the very first frame that you start, it will start at the beginning of a multiframe, like the very first packet you send. But at the moment, you must not lose any of them, or you will lose alignment. So that's something that needs to be implemented. That's why that header has been there and put in place, is because I knew that at some point we might need it, and it was also meant to be able to compensate for lost frames, because we use isochronous transfer, so we could very well lose an entire USB packet, and I wanted to keep alignment, stuff like that. That's why that header is there, but it's never been implemented until now. And I mean, until this code, the last thing that I had read from the issue is that the alignment wasn't needed because there was this 0-0 pattern, and so I figured, okay, so I don't need to implement it in the gateway. Apparently, I just found out apparently I do. So.
Yes, unfortunately. What I didn't understand in the firmware is that story about sometimes there could be only 7 frames and sometimes there could be 9 due to the...
yes, that's in the...
And that makes it a little bit harder to connect the two, but yes.
Yeah, that's because the clock at which we send USB frame is dictated by the clock rate of the PC, right? It's once every USB frame. And obviously that clock of the USB controller is not GPS disciplined. Yes. So at some point, depending if it runs slightly fast or slightly slow, we'll need not to send the nominal 8 frames, but either 7 or 9 to compensate the slow drift that you have between the computer clock and the actual E1 clock. That's why there is 7 or 9.
Yes, and it makes the story with the alignment slightly more difficult, but just slightly, I would say. Or I had the impression when reading it.
Yeah, not really. What the hardest part really is handling lost packets, basically, is that because at the moment we just push them in the FIFO, but if we at some point we notice a discontinuity between the number that we expect and the number that we actually have, we need to somehow push dummy data into the into the hardware to keep alignment, and that's what I mostly needed to see how to deal with. It's nothing super complicated, but yeah, I'll try to have a look at it.
Yeah, but it's only a firmware issue, right? In the gateway, you don't need to change anything.
Yes, no, the gateway you don't need to. The only thing that I was considering changing for the gateway to support that is that at the moment, the firmware almost never deals with the data. It only orders the DMA copy directly from the USB peripheral to the E1 peripheral, basically. But if you need to push a lot of dummy frames because you missed a bunch of USB data packets, the firmware might have to write a lot of data into the E1 buffer, and it's not an especially fast path for it to do that. And so I was considering, okay, maybe it would be worse to have the DMA engine be able to just fill FF, basically. But it's really just a performance optimization in case it turns out that the firmware is too slow to push dummy data. The other option was just we can actually reserve some, like the buffer that we have for the E154 is gigantic. We don't use all of it. And we can easily just pre-fill an entire multi-frame worth of FF at the initialization time. And then when you submit the descriptor of what you want to push to the A1, you just set the pointer to, okay, just read that dummy frame and push that and be done with it.
Yeah, also it doesn't necessarily need to be a dummy frame. It could just be a repeat of some old data. I mean, at that point, basically, it doesn't matter what we transmit, right?
Yeah, true.
So just some random data, as long as the length is okay, just to make sure that we get into alignment again.
Yes.
Ideally, the repetition should come from 16 frames before, because then you're probably not touching any signaling bit. But that's ideal.
Yeah. That gets complicated at some point because you don't know, like the frame that you're missing, it might be in the middle of a multi-frame, right? You might have gotten like 7 frames of your multi-frame and then just missing the 8 next ones, for instance.
Yes, and now you should look back 16. Should.
Yeah.
I'm not saying you must.
Yeah.
But I mean, it's only for TS16, right? So it doesn't necessarily, but yeah, I mean, also the memory should be there to have 16 frames around.
Yeah, or you could keep the last complete multi-frame.
Yes, that's another option, is to not transmit the entire multi-frame if we lose any part of it. That actually might be easier to do. We store a lot of multi-frame. Like the 5.4, I think, is 256 multi-frame.
Oh, wow. Yeah, well, so you have the space to do that.
Or 206 frames? It's like 65 kilobytes, so...
The other discussion is that at some point, if you want to go the route with the Osmo E1D, there needs to be a connect between the frame number that gets transmitted, reordered in the RIFO and all these things, and the multi-frame, etc.
Yeah, I think that's actually the most complicated part is not so much the firmware, it's the first for Osmo E1D client, because at the moment the API offers nothing to have any relationship between.
Yeah, but I mean, for the client, I just wouldn't bother. I would just go for DAHDI. So if you really want to terminate something like that, I would just implement it in the DAHDI driver, and given that DAHDI already has infrastructure for all of this, and we can compare it with a Digium card, I think that's the easier way.
Yeah, okay.
But for the transparent pass-through case, so the implications of what is in case of in this our RIFO and overruns and underruns and things like that.
But the RIFO frame number could not just be a free running counter, but could be taken from the multi-frame or frame number in the multi-frame that the ICE1 USB is transmitting anyway.
But wait, do we because you can also use the E1D in transparent, like in truly transparent mode, where instead of requesting multi-frame alignment, you request frame alignment, basic frame alignment, and then you tell him to not regenerate the first time slot itself, but just transmit what you give it, and then you. Like it will literally transmit whatever you give it, including all the frame alignment signal for the multi-frame and stuff like that. And at that point, it doesn't really care.
Yeah, but what if you have lost packets?
If you have lost packets, that I mean, on the USB link, that will be a problem. On the rifle link, that shouldn't be a problem. We should compensate them, right? We keep the. So yeah, it doesn't solve the problem of lost USB packets for sure. But it's on the Octoy protocol level, we already handle like the RIFO. If we miss a packet, it will fill it with something, right?
Yes, but we don't. I don't think we necessarily guarantee that how can I say the 31 time slots or whatever the 31 bytes of an E1 frame excluding TS0 is reproduced at exactly the same multi-frame or a frame number in the multi-frame at the receiver side.
Oh yeah, we don't transmit TS0 at all, do we?
Yes, okay. We don't. And even if we did, we still don't have a guarantee that it ends up exactly the same way, right?
Yeah, but the frames are numbered one by one, so I'm not too scared. The last, 4 bits of that numbering could come from this frame is in this multi-frame. And then, yes, there is some extra logic to be coded at the end of the RIFO, right? But at the end of the day, then perhaps we would be throwing away 15 time slots that were transmitted just to reach realignment.
I guess let's stop the recording here. We can continue the discussion. Thanks, everyone.